So we're talking about inverse functions. The title of this section is Inverse Functions. And an inverse function has a new symbol that you need to see and be comfortable with, which looks like this. Okay? So it looks like a negative one exponent, but it's not. It's just a symbol they use for an inverse function. It looks like a negative one exponent, but it's not. It's a new symbol for the inverse function. Now, before we can have an inverse, we have to have what we call a one-to-one function. So you see this title, we will notate this as a 1-1. And you'll even see this in a textbook, 1-1, instead of typing or writing all those words, one-to-one functions. To determine if something is a one-to-one function, it must pass a horizontal line test. To be a function, it must pass a vertical line test. To be a one-to-one function, it must also pass the horizontal line test, which means if you can strike a horizontal line and only touch the graph in one place with any horizontal line you strike, then it is one-to-one. So all of these points in this first graph, since I strike a horizontal line and can never touch it but one time, this one is a one-to-one function. This is a one-to-one function because it passes the vertical line test. Now the second graph, this wave, if I draw a horizontal line, I'm going to hit that wave in many locations. I'm going to intersect it. Rather than just one, I touch it many times. So it is not one-to-one. And then the last one, anytime you strike a horizontal line, you will only touch it once. So it is one-to-one. The reason it's important for it to be one-to-one is you cannot have an inverse of a function unless the original function is one-to-one. So your original function must be one-to-one for an inverse to exist. So then it takes me into inverse functions. Now in inverse functions, what they will do is they'll, whoa, something happened. I got sliding all over the place here. Come on. Come on back down. Giving me trouble. So this is going to be a lousy recording. Okay. So to prove something is an inverse function, you have to do the composition. Okay, the composition. And when you perform the composition, algebraically it must equal x. And you actually have to do the composition both directions, f composition g and g composition x, and it has to equal x to prove the functions are inverses of each other. So they start this section by giving you a couple of functions and say, prove if these are inverses of each other or not, which means you have to perform the composition to determine if they are or not. So let's take a look at this first example. They give me f of x is 3x plus 6 and g of x is 1/3 x minus 2, and they say, are these inverses of each other or not? So to do this, you have to do the composition. So I need to compute f composition g of x, and then I also have to compute g composition f of x, and they better both end up algebraically the x variable for them to be inverses of each other. Okay, let's do the f composition g of x first. This would be f of g of x, which means in my square brackets, this would need to be 1/3 x minus 2. So this is f of 1/3 x minus 2. So this means I need to go to my f function, and in place of the x, I put all that stuff that's in those square brackets. So this becomes 3 times stuff in square brackets plus 6. So this is 3 times the 1/3 x minus 2. Now algebraically you would have to distribute, well, 3 times 1/3. What is this doing this to me every time? 3 times 1/3, come back. It's not letting me scroll up. 3 times 1/3, let me do that, is going to be 1x, and 3 times the negative 2 is a negative 6. So negative 6 plus 6 is 0, so this one does equal x, so that's good, that's our goal. That half of it's kind of proven. Now we got to make certain that it works the other direction. So this would be g of f of x, which would be g of, what is f of x? It is 3x plus 6. So now I go to the g function, and wherever there's an x, here's my g function, where that x is, I'm going to replace that x with the stuff I have in the square brackets. So this becomes a 1/3 times 3x plus 6, all minus 2. Now if I distribute the 1/3, 1/3 times 3x is 1x, 1/3 times 6 is 2, and so x plus 2 minus 2 is x, and so hey, it worked. Both of them equaled x, so it worked. They are inverses of each other. They are inverses. And since they are inverses, what they will do is they will rename g of x f inverse of x. Since we have shown that they're inverses of one another, we will rename g of x f inverse of x. Okay, so let's take a look at another example. Part B has the x cubed in it and also the cube root. So we're going to try to see if they're inverses also. Okay, so I have to do f composition g of x, and then I also have to do g composition f of x, and they're both supposed to result in just the variable x. If they end up something like x equaling x minus 2, then they're not inverses. Okay, so let's try this. So this is f of g of x. So this is f of, what is g of x? G of x is the cube root of x plus 1. Okay, I go to the f function, find the x in your f function right here, and I replace that x with that cube root of x plus 1. So this is stuff cubed minus 1, and that stuff is the cube root of x plus 1. So when I cube a cube root, it eliminates the radical, leaving behind x plus 1, and so this works out to be x, which is the goal. So that's good. That's good. Now the other one has to do the same thing to equal x. So here we go to the g of f of x. G of f of x, which will be g of, what in the world is f of x? It is x cubed minus 1. Now go to your g function, and wherever the x is in the g function, you're going to put the stuff which is in the square brackets. So this is going to equal the cube root of all the stuff in the square brackets, x cubed minus 1 plus 1. So underneath this radical now, I have x cubed minus 1 plus 1, which is just x cubed, which is just x. So it works. So yes, they are inverses of each other, because algebraically both compositions equaled x, and now I can rename my g of x as f inverse of x, because they are inverses of each other. Because algebraically they both equaled x. Now when they're not inverses, your ending line might say x plus 3 or 2x plus 5. Then that would not work. Algebraically it has to come down to equal x. Me and this scrolling is not getting along very well today. Okay, so let's take a look at this cool little graph here. And what they want me to do is they want me to graph the inverse of this blue line. So what I'm going to do is I'm going to call this blue line f of x. And I'm going to create the inverse, because when I reflect it over that red line, I'm creating the graph of the inverse. So let's take a look at this lovely reflection. Okay, so this point at the bottom, if I reflect it over the red dashed line, it would be here. This other point, if I reflect it over the dashed line, it would be here. All right, my other point, if I reflect it over the dashed line, it would be here. And the highest point reflected over the red dashed line would be here. So those are those points reflected over the red dashed line. And if I connect them with lines, whatever it's doing, get away, stop that. Okay, then it would be from here, and then here, and then here. There it is. There's a reflection. Now, the line that's reflected that I just created, this will be f inverse of x. Anybody know the equation of that red dashed line? It is y equaling x. So when you reflect something over the line y equaling x, you're creating the graph of the inverse of that function. Now, before I go further, let's take a look at this a little greater depth. Let's take a look at f of x and the names of all those points. That lowest point on the blue line, that would be the point, oh crud. What did I just do? Okay, here we go. Okay, this lowest point on the blue line, it would be the ordered pair -4, -2. And the next point would be -3, +1. The next point would be -2, positive, -1. It would be -1, +2. And then the highest point would be 1, 2, 3, 4. That's the names of all those points. And so I'm going to build a table over here, and I'm going to put these in here. So I have a -4, -2. I have a -3, +1. I have a -1, +2, and a 1, 4. Okay, what about that inverse that I graphed? Let's take a look at its ordered points. Okay. All right, this lowest point on my, I keep touching it, I think, with my hand. Ah! Okay, this lowest point here, if I name it, it is -2, 1, 2, 3, 4, -4. -2, -4. Then I have 1, -3, then I have 2, -1, and then I have 4, 1. Okay, so let's put those in the table. So I have a -2, -4, then I have a 1, -3, 2, -1, and 4, 1. Now take a look at those ordered pairs in that table, and what can you conclude? What happened to every ordered pair? They just switched. They switched. So every ordered pair point on your original function will be flipped, interchanged, to create your inverse. And the graph will be a reflection over the line y equaling x. All right, now that's pretty significant. That's really some really interesting stuff. So we've learned two things. We've learned that to show two functions are inverses, you do the composition. We've learned three things. To graph it, it's a reflection over the line y equaling x. And we've learned that every ordered pair point, the x and y value will interchange between the original function and its inverse. Nothing difficult, but just really interesting. So now, when we go down to look at this next one, now what we're getting ready to do is find the equation of the inverse. In other words, they want me to now come up with this equation. And they give me this process, which is hard to understand until I do an example. So we look at this example where they're given to me that f of x is 2 plus 1/2 x, And step 1 says take it out of function notation and just write this as y equals 2 plus 1/2 x, because that just makes it a little bit easier. Now, to find the inverse, over here, to find the inverse, what I do is I take that original function and I interchange the variables. So where there was a y, I put an x, and where there was an x, I put a y. So where there was a y, I put x, and where there was an x, I now put y for my inverse function. So that's what this says up here is interchange x and y. We just did that. Now it says solve for y. Okay, I've got to solve this thing for y. So first I'm going to subtract 2 off of each side of this equation. And then to solve for y, I multiply everything, 1/2, I multiply everything times 2. So this becomes 2x minus 4 equaling y. This is my inverse function, so I can rename this f inverse of x equals 2x minus 4. And so while you are writing that down, I'm going to change my color over here on this equation. I'm just going to change it and make it blue. All right, so now you have your original function and your inverse. Well, they've already graphed the inverse for me in blue. That's why I changed it out and made it blue. And I'm going to take a look at this graph for a minute here. And I'm going to take a look at some points. On the blue line, which is the f of x line, I have the point -4, 0. I have a point -2, 1. I have a y-intercept of 0, 2. I have another point 1, 3. So I'm just pulling every point that I can pull off the line. And I have the point 4, 4. So here's some points that I have off of the blue line, just because I can see them. -2, 1, 0, 2. It is a 2, 3, thank you. So now my inverse function, I should just be able to switch all those tabled values. So my inverse function should be going through the points 0, -4, 1, -2, 2, 0, 3, 2, and then 4, 4. That should be my inverse function's points. Let's see if this works. 0, -4 is here. 1, -2. 2, 0. 3, 2. And 4, 4. There it is. That is my inverse function graphed.
Where did you get the 4 where you got the 2x minus 4?
I multiplied everything times 2. I multiplied everything in the equation times 2 so I could get rid of the half. Now, looking at this, if I put in that line of reflection, which is going to cut quadrant 1 and quadrant 3 perfectly in half, is that a reflection over that line? Looks pretty darn good, doesn't it? So that's how you find the inverse function, and you graph it just by switching the ordered pairs of the original function. Okay, pretty neat stuff. Not difficult, but most interesting.
If you multiply everything by 2, shouldn't you add that in parentheses with the 2 on the outside?
You can do that if you want to, yeah. Okay, so there's our first example with a graph. Trying to make connections in every way here. Let's do another example very similar to it, which I don't know why it's still number 5. That's my typo. Okay, So in this next example, a one-to-one function is given. So they're careful to tell you that it's one-to-one, so it's okay, it will have an inverse, you're not wasting your time. Because if it's not one-to-one, you cannot have an inverse. Okay, so we want to find the inverse. So the first thing I want to do is I want to rewrite this as y equaling x cubed plus 5. It makes it a lot easier to find my inverse function whenever I've done that. Actually, you know what? I'm going to try to stay consistent with the example above, and I'm going to put this in blue. Okay, so now when I convert to the inverse, and be sure you have these two functions separated. They need to be distant from each other, very clearly distant from each other. So this one would be where there's a y, put x, and where there's an x, put y. There it is. It'd be x equaling y cubed plus 5. Now that I've done that, I need to solve it for y. So I'm going to subtract 5 off of each side of this equation. And then to get the cubed off of y, I need to take the cube root. So I have the cube root of x minus 5 equaling y. And this is my inverse function. So they said find the inverse function. Well, I found it. This is it. This is the equation of my inverse function. Now this time they didn't give me a graph, but I want to graph both of these. So I'm going to go back and graph my original function. I'm just going to pull a table here and graph some points. And I'm just going to make up some x values and figure out the y. So suppose x is negative 2. That's going to be a huge old number. Negative 2 cubed is negative 8 plus 3. That's not too bad, actually. Always a negative 3. Suppose I pick negative 1. Negative 1 cubed is negative 1 plus 5 is 4. If I do 0, it'd be 5. If I do 1, it'd be 6. If I did 2, it would be off my table for sure, off the graph. So let's plot these points. Negative 2, negative 3 is down here. Negative 1, positive 4, that's a big change. 0, 5, and 1, 6. You know what the cubic function, this is just the y equaling x cubed up 5 units. So it's coming up, and it's kind of curving through and then climbing again. So that's my original function in blue. Now, to graph the cube root, this table is real easy to do now. I just interchange all those ordered pairs. So this table is going to be, this is my inverse points. This is going to be a negative 3, negative 2, 4, negative 1, 5, 0, and 6, 1. I just interchange every one of those ordered pairs. So at negative 3, it's negative 2. At 4, it's negative 1. At 5, it's 0. And at 6, it would be 1. So it's going to look something like this.
So where the first points, if you entered y equals x cubes, it's going to give you the whole table for the first points, right?
Well, if you put it in, if you're talking about putting it in your calculator,
Yeah.
you'd have to put x cubed plus 5.
Yeah.
And then, yes, you could see those.
Those
That would be right. That would be exactly right. Here's my y equaling x. Does it look like a reflection over y equaling x?
Yeah.
Looks pretty promising. Looks pretty good. Okay, so now let's do another one. All right, once again they tell me a one-to-one function is given. Write the equation for the inverse, and then they say compare the domain and range. Okay. All right, let's take a look at this. I'll try to stick with blue. Okay, y equals x squared plus 3. Hold on. Y equaling x squared is my U shape, plus 3 is transformed up 3 units. So really, this graph should look like this. But something's up. This piece of information is very important for 2 reasons. If I graph the whole function, this thing is not one-to-one. And if it's not one-to-one, it cannot have an inverse. So something's got to give. So what they do is they say, crud, my quadratics will never be able to have inverses because they're never one-to-one unless I limit it to only half of the graph. If I limit my image of my quadratic function to only half of it, then it would pass the horizontal line test. It would be one-to-one, and it could have an inverse. So that's what they've done. So they say, well, here's my equation, but in order for it to have an inverse, my x has to be greater than or equal to 0. What that means is the domain is from 0 to infinity. So this inequality written as an interval limits your domain, which gives you only half of your parabola, which makes it one-to-one, so it can have an inverse. Okay, so they've got to be very careful with our quadratic equations. So that's the domain. Now the range, because they gave me the graph, I can find the range pretty easily. Remember, this is the point 0, 3. What's the range of this graphed line? My lowest y value is what? 3. So it goes from 3 to infinity. So I'm going to go ahead and start with the given equation and its domain and range. Okay, so now let's play around with the inverse. Okay, so I'm going to come over here in a different color, kind of a different column, a different region of your piece of paper if you don't have two colors. Okay, so to get the equation, where there was y, I put x, and where there was x, I put y. So it's x equaling y squared plus 3. Now I'm supposed to solve it for y. So I subtract 3. And how do I get the square root off the y? Take the square root. Now remember, if you draw the radical, you must put the plus minus in front of it. Now, we know what the square root of x looks like. Square root of x looks something like this, right? And the minus 3 means to the right 3 units. 1, 2, 3 right here. But if it's a plus minus of the square root, not only do I have the top half, but I also have the bottom half of the graph. If it's a plus minus of the radical, where the top half is the positive part of the radical and the bottom half is the negative part of the radical. Now, knowing that the inverse is a reflection of the original function, do I keep the positive square root or the negative square root to be the inverse? Which one is it? It's the positive. So the inverse function is the positive of the square root. That will not always be true. Sometimes it will be the negative. So I only keep the top half of the graph. Now, focusing on the graph of the black line, which I just graphed here, starting at 3, 0, what is the domain of my inverse function? What's my smallest x value? 3. So this domain is 3 to infinity. My range, remember, is my y values. And so my y values are running from 0 to infinity for my inverse function. Now I want you to compare the domains and the ranges of the blue line, which was my original function, and the black line, which is my inverse. What do you see with the domain and range? They just switch. Just like the x and y variables switch, the domains and the ranges will switch. So in other words, the range of the original function equals the domain of the inverse. And the domain of the original function equals the range of the inverse. They switch. They switch. So this is your original function's domain and range, and this is your inverse function's domain and range.
So how do you know if it's going to be like a positive, the square root of a positive versus negative?
You're going to graph it, and you're going to get that vision in your mind of which one is the reflection. So remember, if I put my line of reflection in here, it'd have to be the top only to be a reflection. So you're really getting a visual to get that result, to know which one. You see the visual of it. All right, so lots of interesting connections here. Okay, let's see what's next. Okay, here's another x squared function. Okay, so we don't have a graph. And hopefully you're in pencil because I'm going to erase a little bit. We know y equaling x squared is the little U-shaped thing, and x squared minus 2 is down 2 units. So we know that this graph looks something like this. But that is not 1-to-1. So I have to get rid of half of it. So this is incorrect. This needs to be x greater than or equal to 0. And if it's greater than or equal to 0, then that limits my graph to only the right half, which would make it 1-to-1, permitting it to have an inverse. Okay, so from my graph, which we do from transformations, this is the point 0, -2. So this original function is y equaling x squared minus 2, and looking at its graph, the domain of this original function and the range of this original function by the graph, the domain would be from 0 to infinity, and by the graph, the range would be -2 to infinity. And again, I'm looking at the graph. It's always easiest to look at the graph to find, especially the range. Okay, so the goal now is to come up with the inverse function and its domain and range. Okay, so I'm going to go into, well, I'm doing different colors, but I'm doing them wrong. I'm comparing the pattern, but we'll just have to go with this. All right, so replace the y with x and the x with y. Now I'm going to add 2 to each side. And when I take the square root, I'm supposed to put the plus minus on the radical. We know what this is, the square root function to the left 2 units. Plus minus, the top is the positive, and the negative is on the bottom. Knowing this is a reflection over the line y equaling x, do I keep the top half or the bottom half? Is the inverse the top half or the bottom half of that blue graph? Top half. So I need to erase the bottom half, which means that my inverse function is just the positive version of the radical. Which is graphed. And this point is -2, 0. Okay, now, without looking at the blue graph, without looking at it, the domain of my inverse function is supposed to equal the range of the original. It's supposed to be -2 to infinity. And the range of the inverse function, without looking at the graph, is supposed to be the domain of the original, which was 0 to infinity. So once you write them down just by the pattern, is that true by the graph? Is the domain of my inverse function, my blue line, does it start at an x value of -2? Yes. And the y value starts with 0. So it's confirmed. It's right. And if you want to put in, just for your visual, there's your line of reflection, y equaling x.
How come this one doesn't flip because the domain and range like the other ones do?
It did flip.
Well, I mean, like, remember how, like, you had 0 to infinity and everything, like, infinity or 0?
Here it is down here. This 0 to infinity is 0 to infinity on my range. The domain of my f of x is the range of my inverse.
I see.
So they did flip.
I was pressing.
And now this is a real interesting one. And it's the algebra behind this one is why I really had this example. It's because of the algebra involved in this. Okay, the algebra is different, and you need to be good at this algebraic steps. All right, so I'm going to come in here, and I'm going to write this as a y equaling 3x over x plus 1. And so they're not asking domain or range on this. They're just trying to get the algebra down in computing the inverse function, because it's a little different. Okay, so I'm going to go into the blue. All right, replace the y with x and the x with y. There it is. I'm supposed to now solve for y. So when you solve for y, you're going to cross multiply. So when you cross multiply, you make this over 1. So this becomes x times y plus 1 equaling 1 times 3y. Now ultimately you're solving this thing for y, and y is on both sides of the equation and it's in parentheses. So the first thing you have to do is get it out of the parentheses by distributing the x. So you have xy plus x equaling 3y. Now the goal is to get the y variables on the left and anything that's not a y on the right. So you want to move the x to the other side. What color do I want? You want to move the x to the other side, and you want to move the 3y over by making it negative. So without any more confusion than absolutely necessary, this would be xy minus 3y equaling your negative x. Okay, so I've skipped a few steps there trying to make it not look quite so complex. I hope I succeeded. Okay, now your y terms are on the left side and the left side only. So what you do in this case is you factor the y out. And your last step would be to come in here and to divide off that binomial x minus 3. So you end up with y equaling a negative x over x minus 3. And that is your inverse function. Okay, this is your inverse function. Now graphing this one is quite interesting. And I've got everything in the wrong colors now, okay? But on the blue line, and I'm not sure how to do this, on the blue line, if I can pull any points, like this point here would be what, negative 4, 1, 2, 3, 4. This would be negative 4, 4. And this point would be negative 2, 1, 2, 3, 4, 5, 6. Negative 2, 6. So over here, this line has the points of, I have a negative 4, positive 4, and a negative 2, 6. Now some additional points on that line would be not very many. The origin I can see, and the point 2, 2 I can see. So it has the origin and the point 2, 2. Those are the only 4 points I can really identify from the given graph. So my inverse function in its table, I would have, switching the ordered pairs, 4, negative 4, 6, negative 2, 0, 0, and crud, 2, 2. Those 2 points are not very helpful. But when I do this inverse function, I'm going to try to do it like in navy blue. Okay, so I have the point 4, 1, 2, 3, 4, negative 4, 1, 2, 3, 4. And I have the point 6, negative 2. And so this would be the arch. Okay, this would be the arch from the top right corner, top left corner. That'd be its reflection. And the 0, 0 and the 2, 2 are on the same line, so I'm going to say this is going to come out to look something like this. So my dark blue is the reflection of my light blue over the line of reflection, which would be y equaling x. So that is a pretty wild graph, but it works. Okay, it works. The visual is there, seeing that reflection. The ordered pairs are flipped, and the equation, of course, has changed from the original to the inverse. All right? So what we've learned is that for a function and its inverse, to prove them, you do the composition, and the result better be x. We've also learned that the graphs are reflections over that line y equaling x. We've also learned that every ordered pair will be interchanged in the points. And we've also learned that the x and y variables will be interchanged in the equations. We've learned that the domain and ranges are interchanged for the original function and the inverse. So there's a lot of connections there. Pretty neat stuff.